My name is Brian Keith, and I'm an applications engineer here with TMC. I have a PhD in physics from Clark University. At Clark, I worked with the Novel Magnetic Materials group. There, I was creating quantum antiferromagnets and testing their magnetic properties to aid in the quest for room temperature superconductivity, which is one of the holy grails of physics. After graduate school, I worked in cryogenics for 10 years, and I've been with TMC for the past 2 years. Today, I want to talk about a rapidly growing field in physics, quantum computing. Quantum computers, they take advantage of quantum mechanics, which is an extremely successful fundamental theory in physics that describes the behavior of very small objects at the atomic level or smaller. The theory states that small objects aren't made up of solid particles like billiard balls, but that they're fundamentally wave-like. It is more correct to think of an electron, for instance, as being distributed over a small area of space than having a definite location. That is until you measure it. When you measure or interact with a quantum object, then the object randomly depicts a definite state and starts to behave more like a billiard ball or a particle. Until it's measured, though, it's in a superposition of its possible states. All we know before the measurement is the probability to find the particle in one state or some other state. This is a really weird idea. And why should we believe these weird ideas? Well, 25% of the world's GDP relies on technology based on exploiting the weird ideas in quantum mechanics. Without quantum mechanics, we wouldn't have computers, cell phones, jumbo jets, and so on. So now how do we combine quantum mechanics and computers? Well, in normal computers, a bit can be in one state at a time, either a 0 or a 1. So if you had 2 bits, then they could read out 00, 01, 10, or 11. That's 4 different states, and each state could represent a number, let's say 0, 1, 2, or 3. If you want to do a calculation, let's say you wanted to square that number, then a computer can only do that for one state at a time, so it would have to perform the calculation 4 times. But quantum computers consist of quantum mechanical bits. Those are called qubits. They also have 2 states, 0 and 1, but they actually exist in a superposition of those states. So if you have 2 qubits, then together they exist in a superposition of 00, 01, 10, and 11, and some combination in between even. When you do the same calculation for the qubit, squaring the number, let's say, then you only have to perform the calculation once, not 4 times. If you had a 3rd qubit, you can represent 8 states at once. If you have 20 qubits, you can represent 1,000,000 states. And then if you have 300 qubits, you can represent more states than there are particles in the observable universe. So, as we can guess from that, quantum computers, they can be very powerful, but they're also really finicky. The qubits themselves are in a superposition of states until the outside world interacts with them. What does the outside world interacting look like? Well, it could be just the magnetic field generated from a nearby elevator, or a ray of light, random temperature fluctuations in the room, and floor vibrations. Energy transmitted by any of these sources can easily collapse the qubits. That's when the qubits lose their wave-like nature and become more like particles again. Once they're particles, then they're essentially just like bits in a regular computer. They don't have any benefit. This problem is referred to as the coherence problem. The qubits are only doing their job if they are coherent, and they're coherent as long as they are shielded from the outside world. A huge part of the engineering effort for quantum computing is keeping the environment as isolated as possible from the outside world. All efforts to build an isolated environment revolve around the cryogenic strategy. There are a few competing strategies for maintaining a cold and quiet environment, but the most common approach is to surround a qubit processor with a dilution refrigerator. A dilution refrigerator uses liquid helium to cool the environment. A special process using a diluted mixture of helium-4 and the very rare isotope helium-3 is used to get to temperatures below 1 Kelvin. The average temperature of outer space is about 2.7 Kelvin for comparison. The physics of the dilution is interesting, but not in the scope of this video. A very important point, though, is that helium is a non-renewable resource. When it's released from the Earth, it floats off into space, and it'll just be lost forever, unless it's recaptured here on Earth. And the price of helium is very expensive as a result. And the US government even limits how much helium institutions can purchase each year. The US government has a large supply of helium that it's been stockpiling. It's about $30 a liter for helium-4 and $3,000 a liter for helium-3. Nearly all dilution refrigerators today are termed dry. That means that they usually utilize an actual refrigeration cycle like the refrigerator in your house, but instead of using Freon, the refrigerant is helium. And the refrigeration cycle is very efficient such that the very cold temperatures can be reached. The cycle itself, though, is quite violent. There is high pressure gas moving through braided metal lines and a piston moving forcefully inside the refrigerator. This activity leads to the single biggest downside of these refrigerators, in that they introduce tremendous amounts of vibration into the system. This is where TMC can help. Quite often, the vibrations introduced by a refrigerator will be decoupled from the system and diverted towards the floor through the use of flexible bellows. The floor will then vibrate, so the refrigerator structure, which is mounted to the ground, will still be seeing the diverted vibration through the floor. In my lab, I saw that the frequencies of these vibrations typically have peaks around 1 Hz, 30 Hz, and 60 Hz. But each lab space is different, so a floor vibration survey can reveal what the specific dynamics of the whole system are. We have, TMC engineers. We have field engineers that can come to your facility and actually perform a floor survey, and then we can take that data and suggest how to solve any vibration issues that we find. If the floor has low frequency vibration from half Hertz to 100 Hertz, then TMC's Stasis Quiet Island can help. Stasis Quiet Island consists of our stasis isolators supporting a custom-built 4-inch thick steel platform with dimensions chosen to pick for this specific application. The stasis isolators provide an 87 to 96% floor reduction at 1 Hz and more than 99% reduction at 2 Hz. If the floor has higher frequency vibration, then we can supply a honeycomb optical top, which is essentially a metallic version of the carpenter's torsion box. Along with that, we can supply our gimbal piston air isolators. The air isolators work as a soft spring with resonance frequency of 2 Hz. It provides isolation above this resonance frequency. If high and low frequency are an issue, then our laser table base could be considered, as it mixes our stasis and gimbal piston technologies to provide both high and low frequency isolation. If the setup doesn't allow for decoupling of the refrigerator and the environment, then an electrodamp could be considered. An electrodamp would utilize linear motors to apply forces to the refrigerator itself to counteract the motion directly. We also have our magnetics product line, which is a non-invasive solution that can provide EMI displacement to an entire room if desired, also very important for quantum computing. If none of these examples apply to your setup, just contact the applications team here at TMC. I'm happy to hop on a call with you to discuss any custom application. Thanks for watching.